Partial fractions. Let's look at a simple example. We have 2 over 11 plus 5/7. Let's add them together. We would multiply the first one by 7 over 7 and the next one by 11 over 11 to get 14 plus 55 over 77, which gives us 69 over 77. The idea of partial fractions is to take this fraction 69 over 77 and then write it in terms of some number over 11 and another number over 7, where 11 and 7 are the factors of 77. Let's take a look at what it would be with variables. So we would go 3 times x minus 4 plus 2 times x plus 1 all over x plus 1, x minus 4. And this simplifies to 5x minus 10 over x plus 1 times x minus 4. Let's see how partial fractions is used to do some integrating. What we want to do is take this fraction here and we want to break it up into partial fractions. Now, hopefully we can see that if I tried to let u, if we were trying to think of this as a u substitution and I let u equal the bottom, then we would have 2x minus 3, and it would be difficult to deal with this using 2x minus 3. Could we use the method of the quadratics that we've done? Yes, we could, but this is going to be a lot easier for this particular problem. So what we're going to do is take this fraction, 5x minus 10, and we'll just factor the bottom immediately. And that factors to x plus 1 times x minus 4. And we'll set it equal to a over x plus 1. Actually, I don't need that parenthesis there. Plus some constant over x minus 4. At this point, what we do is multiply everything by the denominator, x plus 1, x minus 4. That will clear them all. And we're left with 5x minus 10 equals a times x minus 4 plus b times x plus 1. Now, there's a couple ways that you can go about doing this. Let's just multiply this out to say ax minus 4a plus bx plus b. And let's look at method 1. Method 1 is going to be equate coefficients. So the method of equating coefficients says if I have two polynomials that are going to be equal, then the number of x's on one side has to equal the number of x's on the other side. And the constants on one side has to equal the constants on the other side. And for whatever power it is, if we had x squareds on one side, it would have to equal the number of x squareds on the other side. What if you have x squareds on one side, but not on the other side? Well, on the side that you don't have them, that means you would have 0 of them. So what I want you to do is actually show me clearly what you are equating. So we're going to start with the x's here. The coefficient on the left side is 5. So we'll say 5 equals, what are the coefficients of x's on the right side? We would have a and then plus b. Now we're going to look at the constant. That's all we have in this problem. We have negative 10, and on the right side we'll have negative 4a plus b. Now we have a system of two equations with two variables. We can solve this. If we subtract, we will have 15 equals 5a. Those ones are gone, so a equals 3. Once we know that a equals 3, we can plug it back into this top equation, and that's going to tell us that b is 2. So we have 3 over x plus 1 plus 2 over x minus 4 is what the original fraction is going to equal. Let's look at a method 2. For this one, what we're going to do is pick a value for x. So when we're looking at, I would say let's start with the first form when we use this method. I'm just going to rewrite it to make it clear. What value could we pick that would be really nice? It'd be good to think about this a little bit. You can pause this just to make sure that you have it. When I'm looking at this, I can see here that if I plug in a 4, this one's going to go away. And that will allow me to solve for b. If I plug in a -1, this part will go away, and that will allow me to solve for a. So if x equals 4, we'll get, I'm just going to write it out to make sure you can see it, and then we have a times 4 minus 4 plus b times 4 plus 1. So we get 10 equals 5b. b is 2. If we did the x equals -1, we get -1 minus 4 plus b times -1 plus 1. So in this one, we'll have -15 equals -5a. a is 3. Now, typically when we're doing problems, we don't want to use exclusively one or the other method. What we really want is to use both of them in combination and see which one helps us the most, so we can solve it quickly. Now, what does this become? We're trying to integrate this. Now we have two fractions that are pretty easy to integrate. This, we have the derivative of the bottom on the top, and we just have a 3 times that. So this will be 3 times the natural log of the absolute value of x plus 1 plus 2 times the natural log of x minus 4. Tack on our plus c, and we're done with that. Let's take a look at some more. Here's a general process for finding the partial fraction decomposition of f over g. First, we have to make sure that the degree of g of x is less than or equal, or if the degree of g of x is less than or equal to the degree of f of x, we have to use long division. The reason why is we need to make sure that this degree on the top is smaller than the degree on the bottom. You can think of it like if I had 5 over 3, first I'd want to take out the whole part, the 1, and then I have this fraction 2/3. Or maybe a better example would be 12 over 10, and then I could work on something like that. After we do that, we're going to factor g of x completely. For each linear factor raised to a power, the partial fraction decomposition is a sub 1 over ax plus b plus a sub 2 over ax plus b plus ... plus a sub n over ax plus b. And what you can think of this is if I had something like, let's see, a number over 3 over 8. And I wanted to say, how can I write this? Maybe even a better one would be 7 over 8. Well, this one is 2 cubed on the bottom. So the ways we can get this fraction are by saying a over 2 plus b over 2 squared plus c over 2 cubed. So we're looking at all the powers from 2 to the 1 all the way at 2 to the power we're looking for. That's what's going on here. So we have Oh, I left off here. This has to be a squared, and this is to the power of n. I'm going to have to do the same thing on this one. Hopefully that's okay. For each quadratic where this is, and this is, as I mentioned here, it's known as an irreducible, where you can't factor it over your standard way of factoring the domain of integers. So we're looking at, instead of this time having just a constant, we're looking at 1 degree less than the bottom. So it'd be ax plus b. And we use subscripts to denote that these are different ones. So we'll have a sub 2x plus b sub 2, etc. Theoretically, if you had a cubic on the bottom, we're not going to do that. Then you would have a quadratic on the top. The top will always be 1 less than whatever the bottom is. Go through the partial fraction decomposition and then integrate. For this problem, what I want you to do is hit pause and actually set this up. Just set up the partial fractions. Don't actually do any worried about integration. But it's just, do you have these ideas down? Assuming you've done that, let's take a look and see what you get. We have this x cubed on the bottom. So what's that mean we're going to do? We're going to say that we have a over x plus b over x squared plus c over x cubed. Plus, now we have a quadratic on the bottom, and that's also raised to the third power. So we'll have x plus 1, and then we'll say dx plus e plus x squared plus 1 squared, and then we'll have fx plus g plus x squared plus 1 cubed hx plus I. Now we have another linear factor, so we'll write x plus 5, and then we have x plus 5 squared. So this would be j, and over here would be k, plus, I'll come down to the bottom. Is this factorable? X squared minus x minus 1? No, there's nothing that's going to multiply to give us -1 that it will add to give us -1. So HIJKL Lx plus m over x squared minus x minus 1 plus n over x minus 2. And that's it for just setting up the partial fraction decomposition. Let's take a look at an example where we're actually going to integrate this time. So what do we have? The degree on the top is 3. The degree on the bottom is 4. So it's already okay. Now we can set up our partial fraction. We will have 5x cubed minus 3x squared plus 7x minus 3, all divided by x squared plus 1 quantity squared. So we're going to set that equal to x squared plus 1, and then we have ax plus b on the top, plus x squared plus 1 quantity squared, and we'll have cx plus d on the top. So our goal right now is we need to find out what a, b, c, and d are. Multiply everything by the fraction, so we will have 5x cubed minus 3x squared plus 7x minus 3 equals ax plus b times x squared plus 1 plus cx plus d. Now what? Well, you can, again, we're going to use the either equating coefficients or plugging in a number. And if I look at this, I could see that when I multiply this out, I'm going to have 1x cubed here, and I'll have 1x squared there. Then I'll have a constant b, and I'll have this coefficient of c. So it looks like the equating coefficients on this one is going to work well. So ax cubed plus bx squared plus ax plus b plus cx plus d. And so that's going to equal this. Now we can equate coefficients, and we can say x cubed, we get 5 equals a. X squared, we get negative 3 equals b. X on the left we have 7, and on the right we have a plus c. Well, since we know that a is 5, that's telling us c is 2. And our constant, we have negative 3 equals b plus d. b is negative 3, so that's telling us d is 0. So this thing now becomes the integral of 5x over x squared plus 1 minus 3 over or 5x minus 3 plus 2x over x squared plus 1 quantity squared. And then I have dx. Recall when we've done this, we've done integrals like this before. What we want to do for there is split this up. I was going to do it immediately. Thought that's probably not the best thing to do. Now what? I can take this 5 out. Actually, we have 3 separate integrals. We're going to have to treat them 3 separate ways for the most part. We have 5 integral of x over x squared plus 1 dx minus 3 over dx over x squared plus 1 plus 2x over x squared plus 1. So here's a question. How come I left the 2 there, but I took all the other constants out? One thing you want to recognize with that is that the derivative of the bottom is on the top. And so we could do a substitution here, but if we realize that this is basically the same as 1 over u squared, or u to the negative 2, this one will end up giving us negative 1 over x squared plus 1. Because the antiderivative of u to the negative 2 would be negative 1u to the negative 1. If you're not convinced on that, do the substitution, let u equal x squared plus 1, and then du would be the 2x dx. Over here, we recognize this as an inverse tangent. So just inverse tan of x. That's a straightforward one. Over here, very similar to the last one, except I don't have the exact derivative. Now recall I showed you kind of instead of doing the exact substitution, what we can do is put the 2 in here. Now we have the derivative of the bottom on the top, but if we do that, we have to take it out as well because we can't change the value of the integral. Now we have 5 halves times the ln of the absolute value of x squared plus 1. Now in this case, the absolute value is not needed, so we'll have parenthesis x squared plus 1. Why isn't it needed? Because x squared plus 1 is always positive. Minus 3 times the inverse tangent of x minus 1 over x squared plus 1. And let's write our plus c's. One last problem. So let's take a look here. What's the first thing you notice? The degree on the top is the same as the degree on the bottom. So that means we need to do long division. It's been a while since you've done long division. So we'll have x cubed plus 4x going into x cubed plus 6x squared plus 3x plus 16. How many times does x cubed plus 4x go into this? It'll be 1 time. So I like to line them up because the 1 is a constant value and 1 times x cubed is x cubed. And then plus 4x, what do? We subtract. So we'll have 6x squared minus x plus 16. Now we have a expression here that has a degree less than our divisor. So we're done with the long division. This integral becomes 1 plus 6x squared minus x plus 16 divided by x cubed plus 4x. So this is really what we're doing. Now let's take this and break it up. The one part will be easy. And we'll have 6x squared minus x plus 16. And we factor this thing to x times x squared plus 4. So this will equal a over x plus bx plus c over x squared plus 4. Multiplied by the denominator, we have 6x squared minus x plus 4 equals a times x squared plus 4 plus bx plus c times x. So what do you think we can do right now? If you notice here, I have x times this expression. If x is 0, then I can get rid of that whole thing, and we get 16 equals 4a, so a is 4. Now if we equate coefficients, and we say the x squared term, for example, over on the left side we'll have 6, on the right side we'll have a, and if we multiplied this out we would have b. Now note, you can't just look at this and think, okay, yeah, I'm going to get a b here, instead of actually multiplying it out and seeing it written down. But it's your choice on what you would like to do. What about the coefficient of x? On the left side it's -1. On the right side, the only place we're going to have an x is from x times a c. So we have c equals -1. Oh, I forgot, since a equals 4, this tells us that b is 2. Now we have our problem, which will be 4 divided by x plus, now we're going to have to do the same thing as on the last problem. We're going to have this expression 2x plus -1. We're going to need to break that up, so we'll have x squared plus 4 minus 1 over x squared plus 4 dx. Integrate each piece separately. We have x plus 4. I was already starting to write my ln there. Plus 4 times the ln of the absolute value of x. Plus, we have the derivative of the bottom on the top. We have the ln of the absolute value of x squared plus 4. Again, that one's always going to be positive as well. Minus, now, do we have the derivative on the top for this one? Oh, this is going to be, no, we don't. This is going to be an inverse tangent. So we can come over here on the side, and you could either treat it using a trig substitution, or you could treat it the way we've done it before. I'll review the way we did it before. We took x squared over 4 plus 1, and then had a 4 on the outside. We factored out that 4. This would end up being x over 2. Let u equal x over 2. So du is 1/2 dx, or 2 du is dx. So we would have 2 du over u squared plus 1 times 1/4. That's going to reduce out, and that will end up giving us a 1/2 inverse tangent of u. So this will be 1/2 inverse tangent of, and what is u? X over 2 plus c, and that is partial fraction decomposition.